Okay, so the other day I had a basketball that I was hanging up here at height A on top of the over the ground. So here's part A. That's it, height A, and then I let it go, and then it fell down here to height B, and so now I'm at this height. So it fell because it felt a force, but the Earth didn't come up and grab it. There was a G field that was there, so let's draw that G field. All right. So remember, it's the direction of force on mass. So that would be, well, this is getting pulled down, so the field points in this direction. So here's my G field. It moves down. When it was up here at point A, it had some gravitational potential energy. Down here, it had some a little bit less potential energy here at UGP, UGA. And so, how much work did the gravity do? Work from A to B is how much energy it had there. Remember, because work changes energy. Ooh, that's got to be an E. There we go. Let's zoom in just a touch here more. There we go. I like that better. So, whoa, where am I going? There we go. Well, how much energy it had? The energy it had at A minus the energy it has at B. And now we have something else here. It's MGHA minus MGHB. Nice and simple, nothing too exciting. Now let's do it in terms of electricity. So now I'm going to have a bunch of negative charges down here. This isn't the Earth. This is negative charges. And now let's draw the E field. My E field. All right, what am I going to get? Well, the E field is the direction of the force on a positive charge. So which way would that be? Well, these are negative charges, so it's going to be attracted. So here's the electrical field. Pointing down. Now let's put a positive charge here up at A. I'm going to let it go. It's going to fall. There we go. Or I'm sorry. Down to here. Over here at B. Gravity's not doing the work. The electric field is doing the work now. So how much work is there? Well, it would be the electrical, E, the arrow. Let's draw that again. The work done is going to be the energy at A minus the energy at B. Now, if I was using some nice symmetry, mass is my stuff over here on Earth. Q is my stuff over here on that side. G is my field strength on this side. Here's my field strength on that side. Well, height is my distance. Height A minus QE height B. So there comes QE my delta. What would you call that? Delta H. Right, the distance that I travel. So now my work is this QE, where again, nothing too exciting. But sometimes we like to do things a little bit differently electrically. Instead of looking at it in just sheer energy, now I can look at it in terms of energy per charge. So let's divide both sides by Q. All right. Both sides by Q and up our D. I think I don't like where this is going right now. Let's step back a little bit. So I'm going to have, let's block this off. There we go. Work equals the potential energy at A minus the potential energy at B. I'm going to divide all of these by Q. However much charge this was originally. This is going to give me something a little bit different that shows up in electricity and this concept of energy per charge. This energy per charge is called the potential. potential. Where'd that N come from? The electrical potential. It's measured in volts. I put little hats on it. Again, those are called serifs. So the energy per charge is volts. So then now I can talk about it in terms of how much energy there is per charge. It's a little bit tricky. It's going to take some time to get used to. So energy per charge times the potential. This is potential energy, by the way. Potential energy per charge gives you the electrical potential. So the symbol for potential is V, again with the hats. So let's write this out. Potential energy is UE, charge is Q, V is B. So now the potential energy, electrical potential, is QV, where V is measured in volts, Q is in coulombs, and energy is measured in joules or other things as well. So let's take a look at this again. So remember, we remember work as force times distance, so usually joules, sometimes Newton meters, but now we have it as QV. So it can be coulombs, coulomb volts, which is tricky. This is a big number, but we can measure in units of electrons. Now this is where it gets nice. So then this becomes the electron volt. Oh, you couldn't see that at all. I'm sorry about that. There we go. Work as force times distance. That's that equals QV. Measure this in joules. The force times distance, Newton meters, and then Coulomb volts, which is better as electron volts. It's just really, really nice. Let's do a problem with it. Well, let's say we have, this is problem number 3 out of your book. I have 120,000 volts between these 2 points. Now I'm going to take an electron. Oh, let's draw the electric field in it first. Draw the electric field. Electric field points this way. But if I put an electron in there, it's going to zing this way. How much work is done in electron volts? So work is QV. How many electrons do I have? 1. How many volts do I have? 120,000 volts. This turns into 120,000 electron volts. Man, that's nice. Well, how much work is done in joules? Well, if we go look up on our sheet here that I'm going to go get, and you can't hear me because I'm moving around, and I got a little bit of time here. Here we go. How much work is done in joules? 1 electron volt is 1.6 times 10 to the minus 19th joules. So 120,000 electron volts times 1.6 times 10 to the minus 19th joules ends up giving me 1.6 times 1.2. That's, shoot, what is 1.6 times 1.2? Where'd my calculator go? Oh, no, I'm going to have to try to figure this out. 1.6 times 1.2. Somebody did this already. 1.2 times 1.6 equals 2.5. There we go. 2.5 times 10 to the minus 14th joules. So that's how many joules. Notice electron volts is a whole lot more exciting. But let me ask some more questions. How much kinetic energy does the electron have now? Well, remember, work causes changes in energy. Gravity is too small. We ignore gravity unless we absolutely have to. So now how much kinetic energy does the electron have? What's the change in energy? How much change in energy? 2.5 times 10 to the minus 14th. Now we can ask, what's the speed of the electron? Well, now I need to know that kinetic energy is 1/2 mv². How much kinetic energy does it have? This much. What's the mass of an electron? to look that up. Mass of the electron is 9.11 times 10 to the negative 31 kilograms. You know the kinetic energy. Your homework. Tell me what the speed is. All right. See you tomorrow.